Hello everyone. I decided to do this via live stream even though I didn't tell anyone about it just because that's what my recording software is set up to do. So I want to talk about the project. First thing first is what order to do the project in. Easy, A, B, C. So you've got everything you need to do part A. On Tuesday, on Thursday we covered things you need for part C. Part B, you're going to be doing some research online to find some TSP heuristics. So first of all, for all of the parts on the autograder, watch in the output for each test case where it says test case, and look for the word hint down here. Because some of the test cases have hints that will say, hey, if you're getting this one wrong, think about this. Or if you're over time on this one, take note of this. Also, for all parts of this project, your output can be different from ours and still be correct. The autograder has a separate program for each part, A, B, C, that is called the judge, that judges if your output is right. And to be right, your output must make sense, even if it isn't in the same order as ours. For instance, if I had a square that had points like this, and the distances here were 1, 1, 1, and 1, and suppose that I generated the MST for this. I might generate an MST and leave out the top one. You might generate an MST and instead leave out the right-hand one. So there's 4 edges that can be left out. Of the 3 edges that are there, you could print them in any order. You could say, oh, I had edge 0, 1, or I had edge 1, 2. And I might say I had edge 2, 3, and then I had edge 0, 1. So the order doesn't matter. The only thing that's important is within a given line, the vertices must be listed in increasing order. So you would never say 3, 2, you would say 2, 3. Now in part A, we did do something in our sample output for part A. We produced the output for that in the order that the edges were marked as true. So that will help you a little bit with debugging so that, if you get the wrong output, you can look at what happened. Now, some hints for part A. Your MST algorithm for part A doesn't need to know anything about normal or medical or border. Don't put that there. Suppose that your MST code calls a helper, whether it's a function or a functor, calls a helper to calculate a distance. If we had something like this, and I say, hey, I would like to connect that one to that one. I'd like to connect A to B. Distance function, the distance functor, distance helper, let's say. Distance helper might say 9.7. Even though it crosses the edge of the medical campus, that's okay. We don't want to get concerned about that. Too hard to detect. So just know if we're going from normal campus to normal campus, the distance helper gives us a number like 9.8. If I went from, say, C to D, over here it would say 2.3. If I ask it for the distance from A to C, it's just going to be returning a double. So what double should it return for A to C? Just return infinity. If your MST algorithm receives a distance of infinity, you don't even check if it's infinity. You just do what the algorithm says and say, oh, is this value better than the best one so far? Oh, no, it's not. And you'll ignore it. So that makes the MST really easy to code up. Don't make it know about the normal, medical, or border locations. Don't worry about trying to put them in like 3 separate containers. Way too much work. Just let the distance helper say infinity when they shouldn't be connected. Now, one thing you can do to help with that is determining if a point is in the normal or medical or border locations can be a little bit complicated. What you could do is when you read the input, you read the X and Y and store the category or the location type or whatever you want to call it there along with it. So you'd have the X and Y locations and you'd have some sort of category, which would be Character would be okay. Better yet would be an enumerated type. Now, when you read the input, resist the urge to have one structure that includes X, Y category and everything that goes in prim. Because if you make one that just has X, Y category, you can have one set of code to read in the input. And then you can have a separate structure for, say, a prims table with the D and K and P, have a vector of the inputs, the X, Y category, have a vector of the prim table stuff. If you need it, you can resize that one like for part A. And that'll keep you from wasting too much memory in parts that don't need a prim table, such as it's like your part B might not need it. When you do your math, it is okay to store the X and the Y as integers. However, you want to make sure you carry out your distance calculations on doubles. And so you could convert them to like a double as you're doing the calculations. Just be aware there can be mistakes. For example, if I had like x1 and x2 are 25,000 and negative 25,000. Well, what's 25,000 minus negative 25,000? 50,000. What's 50,000 squared? Negative 5.5 billion. Because the 50,000 squared overflows an integer and becomes a negative number. So you want to cast it to a double before you finish doing the math on it. Now, when you work on part B, when working on part B, what you want to do is a Google search for heuristics. Well, not just any heuristics, obviously TSP heuristics, traveling salesperson problem, heuristics. The heuristic here is a way of solving a problem that is not necessarily the best solution, but it can be a lot faster than part C. So in part B, we want to stick to things that are O of n squared. If you go longer than that, it'll take too long. If you find a way that's faster than that, it'll probably not be a short enough path. So in part B, you'll lose points if you're wrong, obviously. You'll lose points if you're over on time or memory. But you'll also lose points on part B if your path length is too much longer than ours. You're allowed to be somewhat longer than ours, just like you're allowed to be somewhat over on time or memory. But if you're too far over on your length of your cycle, then you'll start losing points for that. That will not show up in the graph of green and blue, etc. The autograder only knows over time and over memory. This is the over path length is really specific to this project. So if you see just green, you may still be losing points. Make sure you look in the feedback file by clicking on the timestamp link, which is where you'll also see the hints that I mentioned earlier. Now, when you look at the heuristics, all of these heuristics are greedy in some way. What they differ in is how they are greedy, how they make their greedy choice. The simplest greedy is called, excuse me, greedy nearest neighbor. So greedy nearest neighbor, what it does is it picks one point arbitrarily. 0.0 would be fine for that. I pick a point arbitrarily, and then of all the other points, so let's say this is 0. Once I pick 0, then I will pick the closest one, and that gives me an edge. Well, then I've drawn this a little bit badly, I think. I think this one will come out being okay. I wasn't planning ahead for it. Let's add another point or two. Okay, let's add those 2 points. So let's pretend that this down here was the closest point. Then the closest point to that one was over here. And I know my picture's a little off. Let's say the closest point to that one was over here. Then we would go like this, then maybe up here, then maybe over here, and then back to the beginning. Greeting nearest neighbor might produce a bunch of crossings like that, which clearly is not optimal. In fact, greeting nearest neighbor is not good enough. You can add to it, you can follow it up with what's called to-opt, which is outlined in the Project 4 tutorial slide deck. But greeting nearest neighbor plus to-opt is not quite going to get you all the points. It'll get you almost all of them. So if you're happy with that, that's fine. If you want to stop there and do part C and come back to part B, that's great. You just don't want to spend too much time on part B, and you've got to, even if it's over on path length, as long as it's good on time, the time doesn't matter. As long as the path length is reasonable, it'll be okay to start on part C. Now, when you work on part C, first thing there is we gave you the genPerms function. We wrote it as a template, but it doesn't have to stay a template. Once you decide what you're going to put in your path vector, you can make it a specific type and get rid of the template. What you should do is make part C a class. Make part C, make a class, and make genPerms a member function of that class. And the reason you want to do this is genPerms is not a tail recursive function. It's recursive, but not tail recursive. Because of that, every function call has to go onto the stack. If you don't make it a member function, you'll discover you need to add a lot of parameters. Well, that function is going to be called on the order of v factorial times. And if you push 7 things onto the stack v factorial times and I push 1, you're going to be slower, guaranteed. So what you want to do is actually make the size t perm length the only parameter. You want to make the path a member variable. The vertices, anything else will be member variables. What is my best distance I've ever seen? Member variable, it's double. What's the best path I've ever seen? It's a vector of the same thing that path is. And so a lot of those things will be member variables. The only thing you want to pass as a parameter is perm length. And that'll make it faster. So another thing you'd want to add is another double for the running total. And the reason you want that double as a running total is every time you call genPerms, you're probably going to be calling the function to get an estimate of the remaining portion. And that estimate of the remaining portion, well, it also needs to calculate the path length so far. You want to say, hey, is the path length so far plus my estimate of the remaining vertices, is that better than the best so far? Then promising would say true. If you don't have a running total for the path so far, every time you want to generate the path so far, you'll have to sum up edges that you just summed up a moment ago. I had 20 edges in my path, so I summed up 20 things. I add 1 vertex, which means I add 1 edge. Now I sum up 21 things. Then I add 1 more and I sum up 22 things. Well, instead, keep a running total. If you look at the call to, or the code for genPerms, it's got a for loop, it's got a swap statement. I'm going to leave a blank line here. It's got a call to genPerms, which will give it perm length plus 1, and then it's got, I'll leave a gap there, and then it's got another call to swap. Right here, what you want to do is you want to say my current length plus equals the new edge length, let's say. And here you want to say my current length minus equals, well, the same thing. How do you know what that new edge is? Well, remember perm length. Perm length tells you how much of the path vector is fixed. Let's say my path right now contains 0, 2, 5, 7, 6, 4, 3, 1, for example. Okay, and perm length is, let's say right now perm length is 3. That means these vertices are in the path and the rest of them are able to be permuted. Right here, when we make the recursive call, what we're doing is we're saying make 7 part of the fixed portion, which means the edge that we're adding is the one between 5 and 7. So that would be from vertex, perm length is 3, that would be from vertex perm length minus 1 to vertex perm length. That's the length of the edge that we're adding. It's think of it this way. It's the vertex path subscript perm length minus 1 to path subscript perm length, because it's not vertex 2 to vertex 3, it's the vertex in the path at index 2 to the vertex in the path at index 3. That's really important. When you do the code for part C, one of the biggest problems is getting this double indexing right. You've got to always think of, do I really mean vertex I, or do I mean the vertex at path sub I? Now, when you call genPerms for the very first time, there's something you got to do careful here, is that we want to make sure we never start a path at any vertex other than 0. Because if we start, let's say we've got a small one. Let's say I've got a small path, just has 3 vertices. Well, if I have a path that goes 0 to 1, 1 to 2, and 2 to 0, that's the same path as going from 1 to 2, 2 to 0, and 0 back to 1. It's the same path as going from 2 to 0, 0 to 1, and 1 and back to 2. Now, it's also the same as going around in the opposite direction, but that's too hard to worry about. What we want to do is we want to make sure we never start at a vertex other than 0. So the very first time you call genPerms, you want to have the path, P-A-T-H, you want to have the path containing 0, comma, everything else, and you want to call it with perm length equal to 1. That says this is fixed. The very first call to genPerms, this vertex is fixed, and you will never make a call where that's in any other position. And that's important because of time. If I gave you 35 vertices and you don't do this, yours would potentially run 35 factorial, where mine runs 34 factorial. Both terrible, terrible numbers, but yours is 35 times longer. So we don't want to do that. One thing I forgot to mention about the running total is there's another part of genPerms that's above this, which is the if statement up there, which is basically checking if we're a base case. The thing you have to be careful of when you're in the base case is you want to check, is my current path length better than the best so far? And if it is, let's update the best so far. The problem is our line right down here that's been adding to that didn't add enough. Because we started out at perm length equal to 1, we've added the edge from 0 to 1, we added the edge from 1 to 2, from 2 to 3, but we never added the edge to go back from the last thing in the path to vertex 0. So when you've got the if for the base case, you've got to make sure that you add that closing edge check, C-H-E-C-K, check and update the best so far. We check if it's better, and if so, we update it. And then we've got to subtract that closing edge. Whatever we do, we must undo. Think of it as preconditions, postconditions. Before I updated the best so far, I had a certain length. After I'm done updating the best so far and I'm about to return from this base case, I go back to the length I used to have. Same over here when we do the current length plus equals the new edge length. Before that recursive call, I had a distance, a total distance of, say, 53. After the recursive call is done, I've got to go back to a length of 3, not leave it at, say, 58. When this is all done, what should be in your path? Whatever you started with. What should be your current length? Should be 0 or really close to it. That's why we have variables for the best distance we ever saw and the best path we ever saw. And that's what we do in the check and update. If our current path length is better than the best path length ever, we update the best path length ever, and we update the best path ever seen to be equal to the current path. If they're vectors of the same types, you just say best path equals path. Let the vector code figure out the best way to copy that vector. Now, in part C, one of the things that we're going to want to do, I mentioned a little bit a while ago, is we need to get an estimate of the remaining cost. I've got this current cost, and look at the lecture slides, watch the lecture video, look at the tutorial slides. There's 3 parts to a path when we want to know, should we keep going, or is this looking bad? And the example I had in the slides is something like this. I've got A, B, and C are vertices like this, and this is my current path. So right now my path is A, B, C, and some other stuff. The unvisited vertices down here are D, and I may get these in the wrong order, but that's okay, D, E, F, and G. Okay, so we have to get an estimate to say, does this look like a good beginning? Well, we can't look at it, we need numbers to decide. So we've got the real path length, we've got this plus this is our current length. We've got to get an underestimate. Watch the video for why it must be under. We get an MST of this portion. That's in the slides. That these are the black edges up here. I'm not going to change colors because it takes too long on my notepad. Down here, these are the gray edges in the MST. And then we're still under. We need some more edges. We need to connect C to the unvisited and the unvisited back to A. So it kind of looks like a cycle. It goes ABC, unvisited stuff, and goes back to A. Does it look like a path? No, because there's that weird branch because of the MST. Doesn't matter because it's an underestimate. So we've got to get, say, this edge here, for example, and that edge there. Does it matter that they both go to D? No. Could we do a little bit better? Yes, but it's more complicated. Is it worth it? I don't know. You can try it out. But here's where part A comes in. I need this MST of the unvisited vertices. You'll want to say, ooh, let's make an unvisited of the unvisited plus A plus C. Don't do it. Bad idea. You can get poor estimates that way because maybe the best way to connect it is to connect A to C and not connect that one. And now your estimate is under. If your estimate is under, you're going to be too slow and you're not going to get answers in a reasonable amount of time. So don't try to put A and C in the MST. Do the MST of the unvisited, then connect the unvisited to A and the unvisited to C. And watch the lecture video. I talk some more about that. So this is where we have to call part B. When you call part A. We need to call part A to get the MST. However, when we call MST, 2 things are really different. One is that we do not worry about normal versus medical versus border. We just want Euclidean distance. The other thing is that I don't want an MST of all the vertices, I just want an MST of some of them. And every time I call part A, I'm going to want an MST of different vertices, different number of vertices. Like sometimes I'll want these 5, and then I'll want a different 5. I'll want some 4. And so we want to make sure that that handoff succeeds. Ways to go wrong there. If your part A prims table never gets reset, and you say, ooh, I'll just make the prims table the right size. You know, I've got 20 vertices, therefore the prims table is always size 20. But you forget to mark them as all false infinity each time. If some of them are true and have small values, you'll get bad estimates, and you'll say things are promising that aren't, and you'll be way too slow. The other way to go wrong is to say, ooh, I need the MST of A, B, C, D because I've got 4 vertices unvisited. No, I need the MST of D, E, F, G. So you've got to, this is where that double indexing might come into play. I don't look at like vertex I to vertex J, I look at vertex path sub I to vertex path sub J. And every time you subscript something here, you've got to think, is it absolute index? Is it an index into the original vector of vertices, or is it an index into the path? If you fail this handoff from part C to part A, you can get an underestimate and you'll be too slow. You could somehow get an overestimate and then you would prune away the best solution and you'll get wrong answers. If in part C you are seeing both things happen, you're seeing some test cases you get right but they're slow, and other cases you get wrong but they're fast, it's probably the handoff from part C to part A. And so what you can do there is, let's do an example here. Let's say that the optimum output that we gave you is, let's say, we don't care about the number. Let's say the path is 0, 5, 2, 1, 4, 3. Okay, and your output is, let's say, 0, 5, 4, 1, 3, 2. Well, at some point, your program was considering that and decided it was not going to be promising. So what you can do is add in an if statement temporarily that says, oh, if path sub 0 is 0, no, we don't have to do that. If path, because 0 is always 0, we can say if path sub 1 is 5 and path sub 2 is 2, then let's print out some stuff. Let's print out, I'll print out my MST cost, and then I'll print out how many vertices are in the unvisited, which in this case would be 3. And then what I would print out is I would print out the X and the Y for these 3 unvisited vertices. Then what I can do is, if you pay attention to the README that came with the sample files, if this is sample D or sample E, we can take this, run part A on it, and get a number. Let's say up here the MST cost that you outputted was, say, 54.30. And I run part A and it says, oh, this is 32.84. Aha! These do not match. I know something went wrong with my MST. This is a great way to debug it. Other way to help debug it is look in the hints and advice section. The very first paragraph there mentions the Project 4 visualizer. It's a tool that's built into AutoGrader 2. It doesn't exist on AutoGrader 1. And so what you do is you just select from a folder on your computer, you select an input file, you select an output file, you select the mode that matches the output file, like TSP or MST, and you hit visualize and it'll show you a graph. And one thing you could do is you could say, hey, let's open up 2 browsers. In one browser, I'll open up the correct output and plot it. And in the other browser, I'll open up my output and plot that. And then I can like shift between the 2 of them or so put them side by side and look at them and see how they're different. If there's not too many vertices, that can be really helpful. Now, what about part B? Part B helps with part C also. So in part C, before we start generating anything, we could say my best path length is infinity. The problem with that is if our best path length is infinity, everything looks promising. If I had, for instance, some vertices like this, and the order is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If my best path length ever seen is infinity, I would go, Does this look promising? Yeah, this looks great. This is all better than infinity. This is a terrible solution. Instead, what you can do is, instead of an estimate of infinity as your best so far, call part B, call the heuristic, and get its answer. You say, well, that'll take time. Who cares? It's v squared time. We're looking at v factorial. If I can use v squared time up front and save me time later by doing better pruning, it's a win. So we call part B, we get its answer. Both parts of part B's answer are important. Let's say part B went like this. Part B got lucky and got it perfectly right. If you only save the length as your best distance so far and you don't save the best path so far as part B's output, then you'll go to print your output and you'll have a distance, and you'll go to loop through your vector and you'll either print nothing because your best path vector is size 0, or you'll segfault because you try to loop over it even though it's size 0. So when you call part B, remember both things it tells you. They're both really important. The path is important for another reason. I'll let you think about that. Okay, let me see if okay, so that's in my notes file. That's everything I wanted to talk about. So good luck with the project. We'll see you in office hours.